Hello, everyone. My name is Sarah, and I'm a PhD student at University of Claude Bernard Lyon 1. And today I'm pleased to present you our work entitled Context Knowledge-Aware Recognition of Composite Intents in Task-Oriented Human-Bot Conversations. Task-oriented conversational bots, or let's call them chatbots, are systems that are widely used to understand user goal and to fulfill this goal by calling the appropriate backend service. This is a common architecture of chatbots. Generally, we have three main components. We have the first is the natural language understanding, or the NLU. Its purpose is to extract the user intent and the slots from the user utterance. For instance, let's say that the user says, what is the weather like tomorrow in Leuven? So the NLU will extract get weather as an intent and the date and city as slots. Then this information is sent to the dialog manager. The dialog manager checks if the detected intent has all required information or all required slots values. If it is the case, it calls the appropriate service, and the output of this service is sent to the natural language generator to produce a human-like response to the user. Let's focus on the dialog manager. It has two subcomponents, the dialog state tracker and the dialog policy. The dialog state tracker decides how to infer missing values from the context. For example, let's say that here we have the value of the city is missing. So the dialog state tracker will try to infer this value from the context, for example, from the conversation history. Then the dialog policy will decide which next action to do. Let's say that here the DST cannot infer the missing value of city. So the next action will be asking the user for this value, for the value of the city. The work we are presenting today is related to the dialog state tracker. Ideally, the chatbot should ask the user for a missing value only when the dialog state tracker cannot infer it from other sources. However, it is hard to achieve this objective. One of the biggest challenges in chatbots is that the user intent can be complex or composite. To understand what is a composite intent, let's start first by what is a basic intent. In today's chatbot, they generally consider basic and atomic intents where the required slot values are directly extracted from the user utterance. They generally use machine learning and natural language processing techniques to extract these values. For example, they train a model using a set of utterances, a set of annotated utterances that represent that intent. Let's say, for example, we have a user intent called schedule a meeting, and this intent required as a slot the meeting date. So, for example, if the user says, can you schedule a meeting for the 1st of April? Here, the meeting date, the value of the meeting date is directly extracted from the user utterance. However, the user utterances, they don't always follow this simple pattern. Sometimes they can be complex or composite, where the chatbot needs to break this intent down into a list of atomic actions and infer potentially missing values from external sources and not only from the user utterance. If we use the same example, and this time let's say that the user says, can you schedule a meeting for the next public day? Here, a holiday. Here, the next we don't have the value of the meeting date, or we have it, but we have it in an implicit way. So here the chatbot needs first to search for the next public holiday, when will be the next public holiday, to get this value, to use it as a value for the meeting day, to be able to fulfill the user intent. So, using existing machine learning and NLP techniques to recognize composite intent is not trivial. These techniques, they have produced really useful and promising results to recognize basic intents. However, they rely on the availability of a massive amount of annotated data. Using them to recognize composite intent will require costly and hard to acquire training data sets. And also, for instance, each time we will identify a new class of a composite intent, we will need to extend or to produce a new data set, which is not easy to do. So we believe that more advanced and more flexible techniques that cater for composite intent recognition are needed. So in our previous work, we proposed some techniques to represent and reason about composite intent patterns. More specifically, we proposed a state machine model that represent these composite intent patterns during interaction between the user and the services. We also identified a set of composite intent patterns that naturally emerge when the user is conversing with services. For example, we identified the slot value flow, where sometimes a missing value can be extracted from the history of the conversation, from an already fulfilled intent. There is also the nested method, where sometimes a missing value can be inferred by triggering another method. And there is the API calls ordering composite pattern. This one is related to API constraints. So one method must be invoked before another method. So sometimes in APIs, we have some methods. This method requires as input an ID, and this ID is generated by the system. To get the value of this ID, we need to call or to trigger another method in the same API. And there is finally the entity enrichment composite pattern. Here is when we have a missing slot value and we can get it by calling or from an external data service. As an example, let's say that we have a method. This method book a taxi, and it requires as input parameter an address, and the user says, I want to go to Eiffel Tower. Eiffel Tower is not an address, but we can use an external service. For example, we can use Google search to get the address of Eiffel Tower and use it as an input for the book taxi method. So this is what we have done in our previous work. Today, we are presenting a new rule-based approach to recognize different classes of composite intents in a generic way. What we mean by in a generic way is that when we will identify a new class of a composite intent, we can add its rules to the chatbot, and this will allow the chatbot to recognize this class during a conversation. So in this approach, we represent the rule. The rule is expressed over the natural language features and the context features. The natural language features, we extract them using existing NLP and machine learning technique. For example, we use Dialogflow NLU model to extract basic intent and to extract slot values. In addition to this approach, our second contribution is that we devised a context knowledge service to capture the context features. So this service will provide the chatbot with some knowledge that help to recognize and realize the composite intents. So the context knowledge service extracts information from different sources, for example, from the conversation history, from the API and intent schemas, and also from enriched entities. Let's focus on this context knowledge service. It has a context knowledge model and set of services or endpoints. So the context knowledge model consists of the metadata and the data. The metadata is the bot schema. We represent it using the context knowledge graph. And this context knowledge graph has 8 types of nodes and 9 types of relationships. This is an example of a context knowledge graph where the chatbot can extract some knowledge. For example, the chatbot can know that the search restaurant intent is realized by Yelp search business API method. Or for example, we can know that Spotify player depends on Spotify search. So if the user wants to start a playlist, the chatbot needs first to call the Spotify search method to get the ID of this playlist and then start it. And for example, here we have place. It is an entity type, and the bot knows that this entity type can be retrieved from Google Play's search external service. In addition to this graph, there is 2 memories. There is a local context memory. This local context memory keeps track of all information related to user fulfillment during the conversation. For example, it keeps track of user utterances, intents, API calls, alongside API method calls, alongside with their timestamp, inputs, outputs, etc. For the external memory, it keeps track of entities mentions in user utterances. And in addition to this, it keeps track of all information extracted by external services. We have also the set of services or endpoints that exploit this context knowledge service on these memories to capture contextual knowledge. For example, we defined a service called dependent method identification. This is to identify a method that depends on another one. For example, we have the intent start a playlist, and we know that this intent is realized by this method, which is a player, Spotify player. And this method will help us that to invoke the Spotify player, we need first to invoke the Spotify search. So in addition to the context knowledge graph, as we said earlier, our main contribution is the rule-based approach that combines both natural language and context features to recognize the composite intents. And the natural language features are extracted using existing ML and NLP techniques. We use the Dialogflow NLU model, and we defined a set of functions that allow us to extract these features. For example, we defined functions that allow us to identify an intent expressed in a given utterance. And another method is the one that let us to extract a value given a slot and an utterance. In addition to this, we defined a set of context functions. These context functions are built over the context, the graph, and the memories, and they allow us to capture the context features. For example, here we have a method that, given a slot, it returns a set of parameters that are the same as this slot. So this is a definition of the method. We have two clauses. We have the trigger and the action. The trigger are expressed as Boolean conditions over the dialog act and the context functions to recognize the composite intent. If the composite intent is recognized, then we will do the action, which is we will execute a sequence of operations. This is an example of an API calls ordering composite intent defined as a rule. Here we have the trigger and here the action. The trigger has two Boolean conditions. The first one is new intent. This one, it checks if the expressed intent is new intent. And the second one checks if the method that realizes this intent it depends on another one. If it is the case, we get this dependent method, we get the inputs of this dependent method, then we get the value of the ID of this dependent method, and we use it in the current one to fulfill the user intent. To evaluate our approach, we conducted a user study where the main objective was to explore the effectiveness of the context knowledge service and the effectiveness of the composite intent recognizer service. So we conducted a user study where we asked participants to interact with two different chatbots. The first one was the baseline. This chatbot implements the standard dialog manager. We used the dialog manager of Dialogflow. And the second one was improved with the CAiSE and CRS services. So we asked the participants to interact with, to perform 4 tasks with each chatbot, where each task corresponds to a composite intent class. For example, here we have the 4 tasks. The first task is related to the slot value flow intent, where a missing value needs to be extracted from the conversation history. The second task is the one related to API calls intent, where the value of slots needs to be inferred from this dependent method. The third task is related to the entity enrichment, where a missing value can be extracted from an external service. And the fourth one is related to the nested method. So we performed a quantitative analysis where we compared conversations of participants to optimal reference scenarios by considering 3 metrics. The first metric is the number of conversations. The second one is the prompts asking for a missing slot value, and the third one is the slot values correctly inferred. So as you can see here, the DM-CAiSE chatbot is the closest to the optimal performance. This means that the chatbot asks for less questions for missing slot values, and this is thanks to the correct inference of the slot values from different sources and not only from the user utterances. We also compute the performance of detecting correctly the composite intents. And as you can see, the DM-CAiSE chatbot is pretty close to the optimal performance. And this is thanks to the CAiSE and also to the composite intent rules that we identified in this chatbot. So as a conclusion, in this work, we proposed an approach that relies on new rule-based techniques. That this approach is hybrid. It uses what exists to detect or to capture the natural language features, but in addition, it captures context features to allow the recognition and the realization of composite intents. To capture the context features, we devised a context knowledge service, and this service allows us to extract information from different sources, such as conversation history, API intent schemas, and enriched entities. We believe that the presented approach charts novel abstractions that unlock the seamless and the scalable integration of natural language-based conversations with the software-enabled services. Thank you all for your attention, and I'm happy to discuss with you any point and response to your questions.
Thank you, very interesting presentation. I'm a little bit interested in context and all of those things. Thank you. The question would be, it seems to me that your context is more like sort of directly going to data values, say, is the city name Lyon? Contra maybe context, is the context safe city? So the question would be, do you do some kind of post-processing from data to context, or is it more sort of matching the data values to the correct entities in the model, or what's your take on this?
Do you mean how to generate this context?
Right. I mean, so if I would like to have context-safe city, then the city name is not enough. Then I have to see the crime rate or whatever.
The others' relationships.
Yeah.
Yeah. I can show you an example. Where is it? For example, let's say that I want to retrieve a place from the external service. This can be, for example, I'm searching for Eiffel Tower, but I can have, for example, a restaurant called Eiffel Tower here in Leuven. So here, what we use, we call them profile attributes. These profile attributes are defined by the bot developer. And this can allow us to filter by location. For example, the user wants to go to Eiffel Tower, but there is too many Eiffel Towers everywhere. So here, for example, if I know that the user is currently in Paris, so I can take the first results returned by this external service and say, this is Eiffel Tower in Paris, so it's mostly like the monument. So this is how we try to filter. The parameters are needed.
Sorry?
The parameters are in the graph. I didn't.
If they are designed, what if the user asks for something
that doesn't exist?
Yes.
We are not holding this. Yeah.
Of course.
Yeah, yeah.
No restraint. And then when you were presenting, I actually missed that you had here Google Play search, and I was wondering a little bit also in relation to the morning's keynote. Are you grasping, being in this research, who is supposed to hold which data? So when you are asking about the Eiffel Tower,
Mm-hmm.
of course, I guess it's not on the chatbot's supplier to have the data of that kind, but rather through some Google search query.
Yeah.
But is that a challenge where to search data so to avoid redundancy, like not
To recall it again, you mean? Yeah, this is why we have the external memory where we keep track of the informations that we already extracted from the services to reuse them after, to avoid recalling again the service.
My
Yeah.
You started this research, and now when you're doing it, how do you know when you see a chatbot, when you join some online service, if it supports this, what you are proposing in this paper, or it does not support it?
You can interact with this chatbot and try, for example, to
Try with those complex.
yeah, to give some complex, for example, add 2 to 1, do this, then please take these results and add another value. If we try to do this kind of things with existing chatbots like OK Google, Siri, etc., they cannot. Yeah, yeah.
Yes, I have one question. If you are in your table for your, the performance of the model,
Yeah.
the T3 external M3, why is it so much lower?
Yeah, this is because in here we took as a task, we asked participants to book a taxi for a journey in Paris, and we asked them to take from one place to another. The problem is that there are some participants that wrote, for example, Eiffel Tower in the wrong way. They missed the I or something like that, and the NLU couldn't recognize this entity. So this is why it's lower than the others. It's because of the mistake that the user can types during the conversation. To handle it, we need another pattern, let's call it, that first detect if there is an error. If there is an error, try to correct it before send it to the service. Thank you for your question.
And thank you very much for good answers.
Thanks all.